So is there a way around these bottlenecks? How do we deal with these bottlenecks? Well, obviously, if we could go off and buy a pipelined A, we could draw our arcs in some clever way, okay, such that, and we could arrange for some of our arcs to go through the pipeline registers here. Remember, the arcs always represent where the pipeline registers go, and in this case, A had 2 internal pipeline registers, so we just make sure our arcs go through those. And now we can see that a pipeline A will allow us to actually get a clock period of 1 now. And that means we've improved the throughput and managed to keep the latency the same. So if you can go out and buy pipelined elements, you can say, oh, my multiplier is slow. Can I buy a pipeline multiplier? Or I can. And then you can draw the rest of your pipeline registers, taking advantage of the pipeline component. But often, we don't have the option of having a pipelined thing. So what do? We run things in parallel, right? We have this opportunity now to basically have 2 dryers and 1 washer. And what we're going to do is we're going to make multiple copies of the slow unit and interleave them. So the notion is that while we can take the output of the first washer and put it of the washer and put it in the first dryer, we can then run an additional load while the first dryer, the first half of the cycle of the first dryer, we can do another washer load, put it into the second dryer, and now everybody will be busy. You know, we've sort of reached a steady state now where by having 2 dryers and 1 washer, we're able to keep all the machines are busy all the time. So the throughput, okay, is now twice as good. We're getting 1 load of dry laundry every 30 minutes because 1 dryer completes every 30 minutes, having run for the entire 60, but we stagger them. We start dryer 1 on the hour and dryer 2 on the half hour, and we get a new dry load of laundry out every 30 minutes. The latency is still 90 minutes, okay? But by making that slow component, trying to get rid of that bottleneck, we've improved the throughput. Okay, so here we have this C unit, which is the slowest one. And we've already drawn this diagram and discovered it's the problem. We can either find a pipeline version of C, or we can think about a circuit that will allow us to interleave multiple of these slow Cs. And such a circuit I've shown you on this diagram, and I'm not going to puzzle through every nuance of this, spend a while looking at it. But the idea is, first of all, notice there is a register on the output. Okay. There are some latches on the input, and the reason we use latches and registers will become clear, instead of registers will become clear in a moment. The idea is that we're going to actually interleave these 2 C components. So on a particular clock edge, we're going to start the processing of 1 component while the second component is finishing from the previous cycle. And so the component we're starting, we're going to be looking at we're going to be starting a new one, which must mean at the end of the current clock cycle, the other one is going to be finishing up. So you can sort of see that whatever one that we're loading, we're starting the processing down here. So we're starting the process, this particular clock edge, we're starting the processing of C1, okay, and C0 is finishing up. So we're choosing to look at the other output. So we have this little state machine here. This little guy is this little flip-flop with the inverter hooked back is just a little state machine that goes up and down every cycle. So you can see that the Q output looks like a clock signal, except it's at half the frequency. And so we orchestrate with this diagram a way of sort of on the hour and half hour starting our C dryer here. Okay, so we can start a new C processing every 4 nanoseconds, but give it an entire 8, right? So we have these 8 nanosecond chunks that are interleaved at 4 nanosecond offsets. Okay, so you can puzzle through the sort of details of that. But the point I'm trying to make is that this is a neat way of basically interleaving slow components, and it acts like a 2-stage pipeline. It takes 2 clock cycles in order for a particular input to appear on the output of the output register. Okay, so in the first clock cycle, we, at time 0 here, we put in a particular value, and it's busily running while we then load in the second value into the second dryer. And then after the second clock edge, we get our output and start processing the third input. So this interleaved component, if we have an n-way interleaved component, we basically have what appears to be is equivalent to n pipeline stages. This is sort of a neat general technique for doing the right thing. And we can combine the techniques of just regular pipelining and our interleave component, remembering that this guy is equivalent to two-way interleavings, equivalent to 2 pipeline stages. So in fact, we have we're going to make sure that 2 arcs go through this. Both of those registers are built into the interleave unit, so we don't have to add any additional registers to the circuit. And now we come up with a circuit where now the slowest component is this 5-unit thing. This 8 is actually broken into 2 4 nanosecond stages. And so now our throughput is set by the F unit. And our latency is 25 nanoseconds, because there's now 1, 2, 3, 4, 5 registers between the inputs and the outputs. And of course, we can get carried away by now, if we need to have even more laundry, we can now take our fully busy pipeline and simply replicate things. And basically, a combination of pipelining and parallelism go off and get even higher throughput, okay, because we get 2 loads of laundry out every 30 minutes instead of just 1, but the latency is still, there we are. Okay, so, and in fact, the most modern machines combine pipeline processors with multiple cores, and you can get very high throughput.